Superconducting quantum processors operate using microwave qubits at frequencies of a few gigahertz. But transmitting quantum information across long optical fiber networks requires terahertz telecom photons. Bridging this energy gap is a requirement for distributed quantum networking. The standard approach for translating between these domains relies on optomechanical transducers. These devices use a localized mechanical vibration to facilitate the conversion between microwave and optical fields. To protect that mechanical vibration from environmental noise, these transducers are built as suspended nanobeams. These are thin silicon structures anchored by microscopic tethers, physically isolated from their substrate, like a bridge spanning a canyon. This design is like a high-performance engine suspended by thin wires. When it operates, the heat it generates has nowhere to vent, causing the internal temperature to rise continuously. At the microscale, this heating occurs when the transducer is struck by an optical pump laser, which is necessary to drive the transduction process. Because the beam is physically isolated from the surrounding material, it lacks a path for thermal conductivity. The suspended architecture functions as a heat trap. As the silicon absorbs energy from the laser, the temperature spikes. This influx of thermal phonons floods the mechanical mode, causing the quantum state to dissolve into noise before the conversion is complete. The isolation intended to protect the quantum signal is the exact mechanism that causes its thermal destruction. To understand why this heating is so destructive, we have to examine the mathematics of the failure point. This is the optomechanical interaction Hamiltonian. It describes how the optical field, A, couples to the mechanical mode, B, via the coupling parameter G0. Achieving the coupling rates required for efficient transduction necessitates injecting high optical power. This inherently drives up the bath temperature, or T-bath, of the structure. The Bose-Einstein distribution defines how the thermal phonon occupancy, and third, relates to this rising bath temperature. In a suspended beam, the lack of thermal conductance leads to a severe spike in T-bath. This causes the thermal phonon occupancy to grow exponentially. This surge of thermal phonons physically overpowers the mechanical mode, distorting the delicate quantum signal until it is indistinguishable from the background noise. For a transducer to be viable, it must stabilize the T-bath variable without degrading the mechanical resonance required for high-efficiency coupling. Solving the heat trap requires a shift in architecture, abandoning the suspended beam in favor of a release-free design. This is implemented using a silicon-on-sapphire, or SOS, platform. This is the equivalent of taking the overheating engine and bolting it directly to a glacier. The mechanical heat instantly drains into the surrounding mass. Sapphire acts as an extreme cryogenic heat sink, conducting heat away from the silicon waveguide thousands of times more effectively than a suspended beam. This keeps the system at millikelvin temperatures, even when the pump laser is operating at the intensities required for transduction. While it was previously thought that anchoring the silicon would leak the necessary phonons into the substrate, we can now utilize mechanical modes that remain firmly guided on the chip surface. The SOS platform decouples acoustic resonance from thermal isolation, removing the thermal bottleneck that limits suspended devices. With a thermal ground established, we can examine the specific mechanics of the frequency conversion. The process begins when a microwave photon excites a localized surface acoustic wave, or SAW, in the silicon. This acoustic wave creates a dynamic grating that modulates an incoming optical pump photon, embedding the quantum state into an outgoing telecom photon. This transfer depends on strict momentum conservation, known as intermodal phase matching. We map this requirement onto a dispersion curve, where the net momentum difference must equal 0. This tracks the momentum of the optical pump, the wave vector of the surface acoustic wave, and the momentum of the resulting optical signal. When these vectors intersect at a single point on the curve, the system achieves perfect phase matching. This alignment places the device in the resolved sideband regime, which is the optimal state for high-fidelity transduction. In this regime, conversion efficiency scales linearly with cooperativeness. We can increase the power to drive up efficiency without hitting a noise ceiling. In suspended designs, this linear climb would be cut short by thermal noise, long before reaching high efficiency. By achieving phase matching on a thermally stable ground, we can reach internal efficiencies that were previously considered impossible for non-suspended architectures. Beyond the individual chip, The SOS architecture changes the requirements for quantum hardware infrastructure. It allows for a facility where multiple dilution refrigerators are linked via standard optical fiber, exchanging quantum information over long distances. These transducers act as the interface at the edge of the cryostat, providing the low-noise backbone for a distributed network. However, these systems still rely on the cryostat to manage environmental heat. The ultimate goal is to move these transduction nodes out of the dilution refrigerator and into room temperature environments. At room temperature, the transducer must operate while completely immersed in a chaotic ocean of thermal phonon noise. Operating in this environment requires an upgrade from crassive thermal anchoring to an active, dynamic filtering system. This utilizes a concept called chaotic subharmonic scattering. By carving irregular, nonlinear boundaries into the structure, we can create a physical filter for incoming acoustic waves. When broad-spectrum environmental noise hits these boundaries, the nonlinear edges force the phonons to break apart into decoupled subharmonics. They scatter and dissipate before they can reach the center of the device. Only the specific surface acoustic wave required for transduction survives, passing through the filter cleanly. This dynamic scattering prevents ambient noise from coupling with the phase-matched acoustic mode. While challenges like quantum memory and error correction remain, integrating a thermally anchored substrate with active noise filtering addresses a primary bottleneck for ambient transduction. It provides a technical path for connecting quantum nodes at room temperature.